My name is Lauren Budorick, and like they said, I'm an engineer at Figma, previously at Mapbox. And at Mapbox is where I really fell in love with graphics programming. So today I'm talking to you about linear algebra. And I know what you're thinking. I realize it's probably a bit risky of an idea to give a math talk to a conference of 800 people who sign up for a JavaScript conference, but here we are. This is not really a linear algebra talk, actually. And let me preface by saying I'm not an expert at linear algebra, and when you leave here, you won't be either, unless you already are, in which case, I'm sorry. No, you could think of this more as kind of a beginner-friendly graphics talk. I would submit to you maybe even kind of a WebGL evangelism talk wrapped in some math, which is another way of saying I hope you think this is as cool as I do. So graphics programming is pretty accessible these days with WebGL, which is a standardized browser-based graphics programming API. And there's a ton of great material online for learning WebGL these days. But in my experience, one thing they mostly gloss over is this whole black hole that is linear algebra. So they talk a lot about how vertex buffers work, and a lot about how index buffers work, and a lot about shaders. And then they say, you just plug in your projection matrix, and then it works, which is not that helpful if you never took linear algebra, or if you took it and you probably forgot everything because you were haunted by memories of doing a lot of matrix multiplications on paper, and you never understood why you need it in the first place. And the ones that do talk about how matrix math works tend to be pretty full of mathematical notation, and they're not that helpful if you are more of a visual learner or just a skimmer or just a human being. So this talk is meant to bridge that gap. What the heck is a matrix, and how do you use it how do you bend it to your will to make stuff show up on your screen? So I'm going to start by framing the problem a little bit. I assume that maybe some of you have worked with graphics before. Maybe there's a few professionals, some hobbyists. Maybe you've done half of a WebGL tutorial, and then you threw your computer out of a window because you can't make anything show up on your screen. And maybe some of you have never touched it. So I'll start with a pretty basic example, but this is not a comprehensive introduction to WebGL. So this is more of kind of the connective tissue that is matrix math. So I'm going to kind of gloss over some of the fundamentals of graphics, but if you want to talk about that stuff, you can come find me later. So arguably, graphics programming boils down to two things. One is positioning triangles on a screen, and the other is coloring in between them. I realize that may sound a bit reductive because there's lots of interesting complexities in graphics programming, but all of it really kind of boils down to these things. It's stuff like how to create and store triangle data in memory, how to move them around your screen. That's what this talk is about. Or how to pick color values for pixels, stuff like that. So here's a pretty basic example, assuming we don't know linear algebra and we're not going to need it yet. Here's three vertices between which I want to draw one triangle. Those are x, y, z coordinates. So I set it up, and then I can draw this triangle, which is easy enough. And it shows up on our screen. But you may notice that this data is all really clean. They're all pretty small integers. The triangle data, actually, one second. OK, the triangle lines up on the edge of our canvas. The WebGL canvas was before I plugged it into the computer. And the z coordinate here is set to 0 on all of them, so we're not sure how that would work anyway. But most of the data you would want to render in real life is not quite this clean. Also, the fact that these vertex coordinates are all between -1 and 1 is not a coincidence. The space that you get to work with in WebGL is from -1 to 1 inclusive in the x, y, and z dimensions, so everything outside of that is going to be clipped. You can't see it. OK, so say we want to work with a triangle that's not in such a neat box. Here we have the vertex coordinates 0, 10, 10, 0, and 0, 0. I've removed the z coordinate because, as you noticed last time, we used 0 for all of those. So for now, we'll hard code z in our shaders since we're just working in 2 dimensions. So this, as you might imagine, is a pretty big right triangle. This is kind of just the bottom left corner of it. The top is way off that way, and the right is way off that way. But if we wanted to see this whole triangle on our screen, we would have to make it all fit between the coordinates -1 to 1 in 2 dimensions. So maybe we could divide all of our coordinates by 10, and then we would kind of scale the whole triangle down by 10. So now we have these coordinates. That's what it looks like, which is great. But maybe that's not what we really wanted. Maybe we wanted to fill our whole screen. How would we do that? So we could take our new coordinates and multiply them by 2, and then subtract 1. So the zeros become 0 times 2 is 0, minus 1 is -1. And the 1s become 1 times 2 is 2, minus 1 is +1. So that kind of works, right? So now we have this triangle that fills our whole screen, which is great. You could say that we scaled it down a lot, and then we scaled it back up a little bit, and then we moved it, translated it down into the left. Remember those words. But if we go back to our original coordinates, by the way, since we scaled it twice, we could just say we scaled it down by 5 and then subtracted 1 from that scaled triangle. OK, so that works. But that's maybe kind of easy to intuit based on the math when you learn when you're a kid for this example, but it's really kind of a brute force techniques that breaks down after 1 or 2 triangles. And this is the whole problem that we're facing here. In practice, in a graphics application, you would have a lot more than 1 or 2 triangles. You would have thousands or tens of thousands or hundreds of thousands of triangles in a single scene. And it breaks down because, 1, it's really only easy to reason about these kinds of mathematical transformations in really simple cases. If we added a 3rd dimension, or we did kind of complex like rotations or combinations of transformations, it would be kind of harder to figure out that math in our head. Or if we had coordinates that were not so nice and like on the axes and integers like that. So the second reason is that we want to be really careful about doing a ton of mathematical operations on the CPU on every frame in a dynamic application, because you could really bog things down. But there is a better way, and it is linear algebra. So one of the core concepts of linear algebra is this thing called a linear transformation. And a linear transformation is a transformation from one whole vector coordinate space into another. A key concept we should start with here is called a basis vector. And a basis vector represents one unit of measurement isolated along a single dimension. So here in our 2D space we're looking at right now, this is our x basis vector, 1, 0. So it's 1 unit of measurement in the x direction and 0 units of measurement in the y direction. And our y basis vector is 0, 1, which is no movement in the x direction and 1 unit along the y-axis. And I'll set up the rest of the grid here, which will help us in a minute. So like I said, a linear transformation is a method by which we can transform one whole coordinate system into another whole coordinate system. We only have this small grid right now, but I would put it to you that knowing these 2 basis vectors, we could draw this grid infinitely in space, because we know the size of our step along the x-axis, and we know the direction of our x-axis, and we know the size of our step along the y-axis and the direction of our y-axis. So we could continue along these axes and draw a bunch of grid lines and do that forever and ever. So if we wanted to represent a different coordinate system, all we would need for that coordinate system is its basis vectors, and then we could draw a different grid forever and ever and ever. So here are some points that I arbitrarily picked out to represent a new coordinate system. This 0.5, 0.6 is supposed to represent my new x basis vector, and the negative 0.2, 0.4 is supposed to represent my new y basis vector. This is going to become a little bit clearer if I overlay the grid again for our new coordinate system. So here you can see how when we transform the basis vectors and preserve the linearity, which is key in a linear transformation, that grid lines stay parallel and evenly spaced, we're setting up a whole different coordinate system. And the reason we do this is so that we can transform a geometry, which is anything you would want to render in a graphics application, from one coordinate system into another. Here we happen to use a geometry that has the same coordinates as our basis vectors, so we know exactly where they end up. But you could see how this transformed grid is instructive for how we would transform any coordinate into our new coordinate system if you just follow where it ends up on the new grid. So that's the conceptual idea behind how you turn this into this without having to do all that math yourself like we did before. Really quick, I want to show this in matrix notation. So we're working with 2 dimensions right now, so we'll set up a 2 by 2 grid, or a matrix, excuse me. And in a matrix, it's used to represent a spatial transformation. Each column represents one basis vector. So we put our x basis vector, 1, 0, in the left column, and the y basis vector, 0, 1, in the right column. And in our standard space like this, that's called the identity matrix. And it's called the identity matrix because it preserves the identity of anything you multiply by it. So if you multiplied any coordinate times that matrix, the result is the same coordinate you put into it. And then in our transform matrix, we put our new x basis vector in the left column and our new y basis vector in the right column. And that is our transformation matrix for this kind of skewed new coordinate space. We're using 2D space here right now. So all of our z coordinates would have 0. But you could represent this as a 3D matrix if you wanted. You would just add a 3rd column that represents your z basis vector at 0, 1, 1, which it's 0, 1, 1 because that's our standard z basis vector, and we didn't move it at all. It's hard to see our z coordinate right now, but if you'd imagine, it goes straight into the screen. And then we zero out the bottoms of the x and y columns because we didn't do any transformations in the z direction for those basis vectors. So now we also have a 3D transformation matrix. So this is the key concept of this entire thing. That notion of moving a coordinate from where it starts on the first grid to where it ends up on the transformed grid, that happens when you multiply a transformation matrix times any point. So now we can use a single transformation matrix and multiply any coordinate times that matrix, and we'll get its correct position in the new coordinate system for anywhere on this entire grid, which is great. So I could also show some matrix multiplication here, but I assume that some of you are scarred by memories of academic linear algebra, so I'm not going to do that. Also, you don't have to know how to do that, because that's what we have computers for, and they're a lot better at it than we are. Also, whenever I say vector and coordinate, those terms are kind of interchangeable. One is kind of preferred by math people, and one's sort of preferred by graphics people, but they mean the same thing. So yeah, any matrix, transformation matrix, times any vector is the transformed vector in that new coordinate space. Here's one more example where we scaled to a negative number. This is to negative 1/10. So not only does it get a lot smaller, but it also flips across the origin. OK, so that's all well and good for some theory, but why do the math and construct these transformation matrices when we can get JavaScript to do it for us? A couple things I have to preface with here. Most of what you'll work with in 3D graphics is 4-dimensional matrices. The fourth dimension is called the W coordinate. It's useful for things like perspective and scaling and stuff, but like kind of magical. Don't worry about it. It's for your computer's benefit, and you can mostly ignore it. So whenever you see 4-dimensional matrices in 3D graphics, just think of them as representing 3D space. You'll see this map4 a lot here. This is a subset of a matrix library called GL matrix, which is a pretty commonly used matrix library. There are a couple of others, but there's only so much a matrix math library can or should do, so there's not that much to get opinionated about. And most functions in a 4-dimensional matrix library like that work with 3D vectors, so again, you don't have to worry about the fourth dimension very much. Also, it was useful to talk about basis vectors to build up some intuitions about how linear transformations work. And in a simple transformation, if you know your basis vectors, like we did before, you can set up a transformation matrix yourself, and then you don't need a matrix library, and you can just do all the multiplication, which, like I said, happens in the shader. However, the beauty of all this is that you don't need to construct transformation matrices. You can just use this library and understand intuitively how a linear transformation works, so that you'll be able to choose the right tools from this JavaScript library to do all that work for you, and move your graphics around however you see fit. OK, so we're going to get a little bit more dimensional here. I've set up this scene. This is a pretty famous 3D model. It's a Stanford bunny. You can download it on NPM. It's npm install bunny. So it's very easy to use in WebGL applications. If you've worked with graphics before, you may know that there are a few more matrices at play here. For example, I've zoomed out a little bit. And I'm going to leave this grid fixed in place so you can see how the bunny moves relative to 3D space. But we will talk about all that stuff later. For now, just consider the single identity matrix that this bunny lives in, like its starting position. Also, by the way, I realize if you've never done graphics that was a pretty quick leap from a 2D triangle to a fully solid bunny. Allow me to prove to you for a moment that everything in life is made of triangles, even bunnies, or at least approximated. If you squint, you can kind of see that all these mesh parts are just tiny triangles. So back to our bunny. In a typical matrix library, you can do something like this, map4.create, and that will give you an identity matrix. So like I said, an identity matrix preserves the identity of anything you put into it. So this bunny right now, all of its vertex coordinates are multiplied by an identity matrix, so they don't move at all. Also, that multiplication part I'm talking about, where we multiply each vertex coordinate through the matrix, that happens in the shader in the GPU, which is good because it means the GPU is doing all this work. And the GPU is very good at doing lots of small operations in parallel, such as multiplying a matrix and a vector. A shader, by the way, is a program that runs on the GPU. In graphics, we work with two types of shaders, vertex shaders, which run on every vertex of every triangle, and fragment shaders, which run on every pixel in between every vertex in the triangles. But today, whenever I say shader, I'm talking about the vertex shaders, because we're just talking about positioning vertices in space. OK. So I'm going to talk about three really common types of matrix transformations. The first is a translation, and that's what happens when you translate or move a matrix by a vector. In 3D graphics, that vector is a 3-dimensional vector, which is just an array of 3 numbers. So those 3 numbers represent how far to move the matrix in the x, y, and z dimensions, respectively. In JavaScript, that looks kind of like this. The first argument is the output matrix. You can just use an empty array for now. This returns the array in addition to modifying it in place, but it's kind of to make this a little bit more flexible. The second argument is the input matrix. Like I said, we're just starting from the identity matrix in this case, because we're just doing one simple transformation. And then the third argument is the vector to translate by. So here we're moving left 3, down 3, and back by 20. The second common matrix transformation I'll talk about is rotation. That's what happens when you rotate a matrix around an axis by some angle. And the axis, once again, is represented by a 3-component vector when you're working in 3D space. So that's what this looks like. In this case, we're rotating by pi. If you remember trigonometry, that's a half circle around the axis 1, 0, 0. So in that case, this is just the x-axis. So it's kind of flipping horizontally, as you saw, around that horizontal axis. But you can kind of rotate around any axis if you want. And the final matrix transformation I want to talk about is scaling. And that's when you scale or resize a matrix by a vector, not by a scalar. If you resize it by a vector with different vector components, then it will resize differently in different dimensions. So here's an example where we scale a model by a factor of 1/2 in the x dimension. So you could see it kind of shrunk by half horizontally, 1.1 in the y dimension, so it grew a little bit vertically, and then -0.3 in the z dimension, so it flattened and also inverted across the z-axis, which is kind of funky looking. Okay. So you can do a couple of other things with the matrix library, but those are some really good core building blocks to start out with. And now we can talk about how to put those together. The first thing to note in putting together different matrix transformations is that order matters. Matrix multiplication is not commutative, which is to say that A times B does not yield the same result as B times A. So we'll look at a few examples to demonstrate. Here's an example in which we translate left and back by 10 each, and then scale down by a factor of 0.3 in every dimension. And I've animated this in such a way that you can see it do these things in order. So when I say do transformation A and then do transformation B, you can think of this in a couple different ways. The first is in this sort of JavaScript pseudocode functiony notation, where the transformation we want first is going to be the inner function, that translate, because first we want to do the translation, and then apply the outer function, in this case the scaling, to the result of the entire first transformation. The other way you can think about this is in matrix multiplication form. Just like in function notation, we kind of work from the right to the left. So first, you translate, and then you go left from there and do the scaling. You would see matrix multiplication notation like this if you use multiple matrices in a shader, which is pretty common in practice. And then here's a different transformation. We did the same things, but in the opposite order. So here, first, we scaled down by a factor of 3 each, and then translated left and back by 10. So now we make the translation the outer function because it's last, or we put it on the left in multiplication notation. Here I've overlaid both of these transformations on the same grid. They started from the same place, and they do not end in the same place, as you can see. So you can tell that order really does make a difference. If you think about it, maybe this is kind of intuitive. In one case, we're translating by some amount, and in another case, we're translating by a scaled down version of that amount. So it kind of should end up different. So we'll talk about more ways to combine multiple matrices in graphics. This is a pretty standard paradigm in 3D graphics, the model view projection paradigm. And it's the idea of computing 3 separate matrices for any object in a scene. The model matrix represents the object, the view matrix represents the camera or viewer, and the projection matrix is what projects world space coordinates into clip space, which is sort of the most confusing one, but we'll get through it. So a model matrix, like I said, is meant to represent an individual object model. This is useful if you have multiple different objects in a scene and you want them to move independently of each other. So each of these bunnies has its own model matrix that's moving independently. One is doing this continuous rotation and the other is doing kind of a continuous scaling. In this case, they're both using only one type of transformation, but you could combine any amount of transformations and move these models however you wanted. The view matrix is meant to represent the camera or a viewer. Here, the camera itself is rotating around the model, so it kind of looks like the bunnies and the grid, everything in the scene is fixed in one place, and we, the viewer, are the only thing rotating. And that's because all these models use the same view matrix, because we want them all to be in the same camera space. It doesn't have to be rotation, of course. You could do any kind of zooming, panning, flyover type of animation you wanted. And the projection matrix is sort of the harder one to understand. For a projection matrix, we usually use something called perspective projection, which sets up a scene with perspective, which is where objects that are further away from you appear smaller. That is how humans see. And that's what makes grid lines converge in the distance right now. And then when it looks like that, that's an orthogonal projection, which is sort of the opposite of a perspective projection, where objects further away have the same size. So it kind of looks like we're zooming into this, but actually the objects in the scene have the same z distance away from us, and we're just no longer applying perspective, so they just don't appear smaller because they're farther away. So it's kind of hard to wrap your mind around that because humans just can't see like that, but that's what's happening. It's also very weird to tween between perspective and orthogonal projection like this. You wouldn't usually do that, but just for demonstration purposes. It should also now be clear that all of the examples I've used so far, all the 3D examples at least, have employed a perspective projection matrix because, like I said, humans can really only make sense of 3D things when they look small or farther away. And also, like I said at the beginning, they all employed a view matrix that kind of zoomed out by a little bit so that we could see everything. So now that I've talked about these 3 types of matrices, this is actually what was happening in the original not moving bunny matrix. There was a model matrix, which is the identity matrix. So it's not transformed at all. And then the view matrix moves, like, kind of moves everything back by 3 and down by 3, and the perspective matrix is a standard perspective matrix, projection matrix, excuse me. Remember that order matters. So when we say model view projection, that is in order. You want to first apply the model matrix, and then the view matrix, and then the projection matrix. This kind of makes sense if you think about it intuitively again, because if you have one model matrix that does the scaling and one model matrix that doesn't, and you apply these backwards, then you would be applying the projection matrix, which is meant to represent the entire world, and then scaling it for one thing, and then not scaling the whole world for another thing, so they're not really in the same world anymore. Again, that's how that looks in outside-in function notation, or right to left in multiplication order. Or here's how it would actually look if we were to use it in a vertex shader. In blue, those are our matrices, and then on the right is our vertex position. This is kind of our dynamic per vertex input. So we'll multiply from right to left. First, we project the vertex into model space, and then we project that whole thing into view space. Then we project that whole thing through the projection matrix into into clip space. And then our final output is this vertex projected into clip space or screen space. A couple of things, tips, tricks, caveats from my personal experience. This can often feel like more of an art than a science. There might be a few like really hardline math people who would say that this is a little bit more deterministic than I'm saying. But in my experience, it takes some trial and error just to get something to show up on your screen when you're first working with graphics. That's totally normal. I consider myself pretty proficient in graphics, and even when making these slides, I several times messed up the transformation orders and had bunnies rotating in giant axes, which I was not expecting. Also, when it's in doubt, you should assume that maybe it's backwards. Even if you can't quite grok why it's backwards, just try flipping the transformations, and it will. It's a good place to start. JavaScript is cheap. Console debugging is your friend. Shader debugging is not your friend. So sometimes if you can't get something to show up, you will be surprised to find that your matrix is filled with not a number. That would be helpful to know. And if it is a valid-looking matrix, you can kind of plug it into your REPL and do some matrix multiplication there using a matrix library to figure out where your coordinates are going if you can't see them through your shader. Something like this, doing like a tweening or interpolation, is also your friend. This is how I did all the animation in these slides. So if a model has disappeared off your screen and you don't know where it went, you can try animating by tweening between a known on-screen matrix and something that is off-screen that you can't find. So at least you know which way it went off your screen. It sounds like we're chasing literal bunnies, which I think is kind of hilarious. My last tip ties into my acknowledgements. All of the graphics in this presentation were done using Regal, which is this awesome functional WebGL abstraction library. If you find yourself wanting to try some WebGL after this, and you go look for the documentation for WebGL and you want to scream, I recommend that you try Regal. It's pretty awesome. These slides were done using Big. The matrix library is GL Matrix. All those things are on NPM. And this YouTube series is the reason I know all the linear algebra I know, because I never took it in school, and I think it's great. So that's all I got. Thank you. Thank you.